Hello students, this is lecture number 9 of digital signal processing, and in this lecture we are going to discuss about the stability of linear time invariant systems. So stability is always the first and the fundamental question in designing the systems. Those who have studied linear control systems in last semester, and they know very well uh, how important the stability of a system is. So stability basically, when you practically implement the system, it plays a vital role in accuracy of the outcome of the system. So an LTI system is said to be stable if and only if output sequence y of n is bounded for every input sequence x of n. Right? So bounded means it remains within the defined limits. Right? So when a bounded input is applied, the output of the system should also be bounded. Otherwise, the system is said to be unstable. So what is a bounded sequence? A bounded sequence is a sequence which has certain limit. For example, x of n is said to be bounded sequence if there exists a constant, let's say mx, such that the magnitude of the sequence is less than or equal to the defined limit mx, and obviously it should be less than infinity. For example, if a DC motor has maximum input voltage 24 volt, which is the upper bound, right, after which the saturation occurs. So 24 volt we can say is the mx. Right. Similarly, when you are driving a vehicle on a highway, then the speed limit at the highway can be considered as the upper bound. Right. So your input signal, your throttle signal, should not exceed such that the upper bound is crossed. Right. So when we apply input to the systems, we define some boundaries, and when the signal or the response of the system cross these boundaries, then we call these systems as unstable system, and as long as they remain within these boundaries, we call these sequences or the responses as the bounded. Now in this slide I am going to give you some examples of bounded sequences and unbounded sequences as well. Right? So step sequence, you all know it's a very familiar input signal which is applied to test the transient response of the system. So x of n equal to a when n is greater than or equal to 0. So is it bounded or unbounded? Of course it is bounded, because it has constant magnitude when even though n increases towards infinity. Right? So that step sequence is a bounded signal. Right? And what about rising exponential? So as the name indicates, it is rising exponential, and it would continue to increase as n reaches infinity. Right? So its final value is not defined, it would continue to grow towards infinity. Therefore a rising exponential is an unbounded sequence. Then decaying exponential, obviously the final value of the decaying exponential is 0. Right? So when n reaches infinity, x of n would be 0. So it is a bounded sequence. Right? Ramp function, x of n equal to n when n is greater than or equal to 0. So this signal also increases when n reaches infinity, its value will be infinity as well. Right? So the difference between rising exponential and the ramp function is ramp function increases linearly and rising exponential grows exponentially. Final value of the both function is infinity, and they are always increasing, and therefore both are unbounded. Then we have sinusoidal function. Sinusoidal function can be represented mathematically by this equation: x of n equal to a cos omega naught n plus theta. So A is the amplitude, maximum amplitude. Right? So since maximum amplitude of this function remains constant, although instantaneous value may change, right? But the maximum amplitude remains same. It remains within the boundary, whatever it is. Therefore, the sinusoidal signal is also referred to as a bounded signal. Then we have another function which is combination of sinusoidal and exponential function 2 power n. Now this signal is actually product of 2 power n and cos omega naught n plus theta. So cos part of this function is bounded. However, this function 2 power n is not bounded. It increases as the n reaches infinity. Right? Therefore, we can call this entire function now bounded output. So we can define the boundedness of the output or the response of the system in a similar way we define the boundedness of the sequence. So if a bounded input x of n is applied to a system, then if the system is stable, then output of the system or the response of the system should also be bounded. Let's represent the boundary of output or upper bound of the output by my. Right? So y of n is the response of the signal, and it should be equal to or less than, the magnitude of y of n should be less than or equal to the upper bound, and of course it should be less than infinity. For example, again, if a DC motor has maximum input voltage 24 volt, which is the upper bound, then mx is equal to 24 volt, and this is the bounded signal which can be applied to the input of the motor, and the response of the system, for example, RPMs at 24 volt should be 5000 RPMs. Then my, the upper bound in the response of the system, is 5000 RPM, and these are, we can say, the limits or the boundaries in input and output sequence. Input sequence, the boundary is 24 volt, and the output boundary is 5000 RPM for this particular example. Now some examples of bounded and unbounded responses. For example, y of n is equal to x of n minus 1, where x of n is a bounded sequence, right? So obviously y of n is also bounded because x of n is also bounded, and this kind of system is called unit delay function, a unit delay system which only introduces delay in the system. Right? So this system, the response of the system is bounded when x of n is bounded, and here x of n is bounded and y of n is basically cosine of x of n. Right? So since x of n is bounded, then cosine of x of n will also be bounded because cos function itself is bounded. Right? So this makes y of n also bounded. Then y of n equal to u of n to x of n. U of n is the unit step function and x of n is some bounded sequence. Right? So u of n is also bounded, right? X of n is also bounded, and the product of these two functions would also be bounded. Therefore, y of n is also bounded. Then we have x of n equal to y of n equal to natural log of x of n. So x of n is bounded, but natural log of x of n may not be bounded because natural log of a sequence can result in an increasing sequence, right? So y of n in this case can be unbounded. Now let us establish under what circumstances or condition an LTI system would be stable. Right? For that, let us suppose a bounded sequence x of n is applied as an input to an LTI system, and we know we can calculate the response of the system using convolution sum given by this equation, right? So when x of n, a bounded sequence, is applied as an input, the y of n computed using this formula, where h of k is the unit impulse response of the system and x of n minus k is the bounded input sequence that is applied as an input, right? Now if the system is stable, then y of n must also be bounded. So in order to check whether y of n is bounded or not, let us find out the absolute value of both sides of the equation, right? The absolute value of y of n would be equal to absolute value of this summation. Now the absolute value of sum of terms is always less than or equal to sum of the absolute values of the terms. Therefore we can actually rewrite this equation in this form, right? Here the absolute value of the sum of the terms were written, and here sum of the absolute value of the terms are written, right? So it is always equal to or less than, right? So y of n would be less than or equal to sum of the absolute values of the terms. Now x of n minus k, this is already a bounded signal that we assumed in the last slide, right? So since input x of n is already bounded, there exists a finite number mx such that the magnitude of x of n is less than or equal to mx, and it is less than infinity, right? So mx is the upper bound of x of n minus k, right? So let us substitute this value, the upper bound, in this summation sign instead of x of n minus k. After substituting the value of upper bound instead of input signal, we get this equation, y of n equal less than equal to mx and summation of h of k from minus infinity to infinity. Now this outcome, the product of mx and this summation sign, can be bounded if and only if h of k, summation of h of k from minus infinity to infinity is bounded, because we know mx is already bounded, right? So only condition that can satisfy boundedness is that this summation is bounded, right? So we can say from this expression that output is bounded if impulse response of the system is bounded, right? Or mathematically it can be written in this form. So sh is defined as k equal to from minus infinity to infinity, h of k should be less than infinity, and this is the condition of boundedness for the response of the system. So a linear time invariant system is stable if its impulse response is absolutely summable. This condition is not only sufficient for stability but also necessary to ensure the stability of the system. If any LTI system doesn't satisfy this condition, that system is simply unstable. Now let's solve an example to understand what we have discussed in previous slides. Impulse response of a certain system is given, and we have to determine the range of values of parameter a for which the system is stable, right? So h of n in this example is equal to a power n into u of n, where u of n is unit step function, and we know very well unit step function is non-zero when n is greater than or equal to 0, and it is 0 elsewhere, right? So it is a causal system, right? The impulse response is a causal response. It is equal to 0 when n is less than 0, right? So since the system is causal, the lower index of the summation can be simplified, and we can start at k equal to 0 to infinity instead of starting from minus infinity to infinity, right? So we can write down the condition of stability in this form, sh defined as k equal to 0 to infinity, h of k and should be less than infinity, right? Now substitute the value. Instead of h of k, we are going to write a power n, and since u of n is equal to 1, so we no need to write this in this equation again. So as h defined is k equal to 0 to infinity a power k, and should be less than infinity. Now let us expand this summation sign by substituting different values of k starting from k equal to 0. So when k is equal to 0, the absolute value of a power 0 would be equal to 1, and similarly when k is equal to 1, we'll get absolute value of a. When k is equal to 2, we'll get square of the absolute value of a, and so on. So this sequence in short can be written in this form as h equal to 1 minus absolute value of a plus k plus 1 divided by 1 minus absolute value of a. Now the final value of this function can be determined when we allow k to reach infinity, right? So when we allow k to reach infinity, the final value of s would be equal to 1 upon 1 minus a, only if the magnitude of a is less than 1, the absolute value of a is less than 1, otherwise it would be a divergent sequence, right? So the only condition for convergence of the sequence is that the absolute value of a is less than 1, otherwise the limit of the sequence when k reaches infinity won't be converging, right? Therefore we can say the system is stable when absolute value of a is less than 1, and this is the value of the boundary condition. Now another similar example in which we are given the impulse response of the system, and we have to determine the range of values of a and b for which the system is stable. Now in this case, h of n is equal to a power n when n is greater than or equal to 0, and it is equal to b of b power n when n is less than 0. So this system is not causal because it has values from minus infinity to infinity. So the system is non-causal. Therefore we can actually break the summation into two components, one which starts from k equal to 0 to infinity, and other when k is from minus infinity to minus 1, right? So this is the part when n is greater than or equal to 0, and this is the part when n is less than 0. So substituting the values, h of n is equal to a power n when n is 0 to infinity, or k is from 0 to infinity, and it is equal to b power k when k is from minus infinity to minus 1. Now we already know that what the condition of this part, right? This is exactly the same problem or same summation that we did in the example number 1, right? So for this part we know the condition for stability is that the absolute value of a should be less than 1. Now let us focus on the second part, the other part. Now let us expand the second summation term, and after expanding we can rewrite the equation in this form where k is varied from minus 1 to minus infinity, right? So first the value of k is minus 1, then minus 2, then minus 3, and so on until k equal to minus infinity. Now we can further simplify this equation in this form by writing the negative powers in reciprocal form. So absolute value of b power minus 1 can be written as 1 upon absolute value of b, and so on. Now we can simplify it even further by taking 1 upon absolute value of b common. So taking common this value, we can rewrite this sequence in this form. Now let us assume that for simplicity 1 upon absolute value of b is equal to beta, right? Suppose beta is equal to 1 upon absolute value of b, so we can rewrite this equation as 1 upon absolute value of b is simply beta, then 1 plus beta square plus so on. Now this sequence is exactly the same sequence as given in the, so this is a similar sequence as we obtained in the first part of this problem, and multiply by beta, of course. So we can write down the summation in short in this form: beta equal to 1 upon minus beta, right? So the condition for convergence for this part is that beta or equal to 1 upon absolute value of b must be less than unity, otherwise the sequence would not converge. So therefore the system is stable if b, absolute value of b is greater than 1 and absolute value of a is less than 1. So these are the conditions for stability for the system given by the impulse response in the previous slide. Here is an exercise problem for you, and in this problem you have to determine the range of value of parameter a for which the LTI system is stable. The pulse response of the system is given by this equation: h of n equal to a power n when n is greater than or equal to 0 and n is even, right? And it is equal to 0 otherwise. So this system is causal and slightly different than we did in the first example. So that is end of the lecture number 9, and if you have any queries you can contact me using my email address given in the first slide. Thank you very much.